Welcome back to Physics 152. This last part of this section of the course dealing with sound waves is all about the Doppler effect. And even if you haven't necessarily heard that phrase before, this is probably a familiar physical phenomenon to you. I'll explain in just a minute. But this phenomenon is also very useful in applications for indirectly measuring the speed of objects that are sometimes difficult to view directly. So, the examples include the fetal heart rate monitor, Doppler weather radar for tracking the motion of atmospheric phenomena, police radar for measuring the speeds of moving vehicles, a baseball jugs gun to measure the speed of a pitcher throwing the ball toward the plate, and, in science, being able to measure the speed of distant galaxies. And this is the most direct evidence that we have for the expansion of the universe. The basic concept in the Doppler effect is that the frequency of a wave that's emitted by a source depends on the speed of both the wave source and the listener. And so we're going to work out some very simple equations that will apply to the one-dimensional case where the source and the listener are either moving directly towards one another or directly away from one another. So, the kind of situation where you've probably observed this before has been if you've ever been stopped at a railroad crossing and heard a train blow its whistle as it approaches you, and then perhaps as it moves away from you. And what you'll notice is a change in the pitch of the train's whistle as it changes from coming towards you to going away from you after it's passed. And that change in pitch can be explained by considering what effect the motion of either the source or the listener has on the waves. The qualitative rules that we have to remember in order to correctly apply the equations that we're going to derive go like this. If the motion of the listener is towards the source, or the motion of the source is towards the listener, that's going to cause the frequency to go up. And conversely, if the motion of the listener is away from the source, or the motion of the source is away from the listener, that's going to cause the frequency to go down. And so what we're going to do is very briefly analyze these two cases separately. One being the motion of the source, and the second being the motion of the listener. And then we'll get two separate equations that we can combine into one general equation that will cover all situations. So here is a simple picture showing wave crests that are emitted by a moving source. The dots on the left side indicate the position of a source at equal time intervals, and what happens at each one of these times, it emits a wave pulse. And then those wave pulses, since they travel in all directions, we're going to indicate those as being on the surface of a circle. And so you can see that the first wave pulse, the largest circle, was emitted by the source when it was at the leftmost point, and the last wave source, the smallest circle, was emitted by the source when it's at the rightmost point. So the effect is, as you can see, that since the source moves to the right as it's emitting these waves, the wavelengths, which is the distance between these wave crests, gets smaller in front of the source and larger behind the source compared to the way it would be if the source were just at rest. And so what happens then is the listener who's doing the measuring measures a shorter wavelength. And so we can describe how much that wavelength gets shorter by thinking about what is this extra distance that's traveled by the source from one moment to the next in between the different wave pulses being emitted. And that's a pretty straightforward thing to do. In between those emission of those successive wave crests, the source travels a distance equal to its speed times the time in between the wave crests being emitted, and that time we call the wave period. So that's the amount by which the wavelength is shortened compared to what it would be if the source were at rest. So lambda prime, the shortened wavelength, is equal to lambda which is the wavelength we would have if there was no motion, minus this distance traveled by the source. So we can now calculate the new frequency, and we'll call it f prime, the Doppler-shifted frequency, for this case of a moving source. It's v over lambda prime, and now we substitute for lambda prime, and realize then that we can factor out a lambda from both terms in the denominator, so we get lambda times 1 minus vs times the period over lambda, and now we realize that t in this expression is equal to 1 over the frequency, right? And so in that term in the denominator, 1 over the frequency puts the frequency in the denominator multiplied by the wavelength. Frequency times wavelength is just the wave speed, the wave velocity. And what we see also is v over lambda is equal to the frequency f. And that frequency f is the frequency that would be measured if the source were not moving. So both those simplifications give us something here that we can now do one more thing to simplify by multiplying the top and the bottom by the wave speed v. So we get f prime is equal to f times v over v minus v sub s. So remember what this is telling us. V is the velocity of the waves, and so if this is sound waves, v would be whatever the sound wave speed would be. Vs is the source velocity. F is the original frequency when there's no motion, and then f prime is the frequency measured by the listener. And you can see in this case what we have is a fraction where the denominator is smaller than the numerator because of the minus sign, which means that this term will end up being greater than 1. So f prime will be greater than f. And the only difference we would have if the source was moving away from the listener is that the wavelength would get larger, so the minus sign would turn into a plus sign, and the denominator would be v plus v sub s. Alright, so for that case of the source moving towards the listener, this is our master equation, and we would just put a plus or a minus sign into that term in the denominator. Now let's work through the case of a moving listener, a listener who's moving towards a stationary source. And now you can see the wave crests emitted by the stationary source have the same center. And so the initial one has traveled all the way to the outer circle, and then a short time later a second one is emitted, and then a third and a fourth and a fifth, shown with these concentric circles. Well, the listener in between each of those wave emissions has moved to the left at a speed v sub l. And in this case we can see the wavelength that the listener would measure is not affected, right? Because the listener's motion doesn't change the distance between those wave crests. So what happens? What causes the frequency change in this case? Because indeed it turns out that the frequency, when the listener approaches the source, the frequency is going to be shifted upward. But what's the origin of this? Well, here's what happens. In the frame of reference of the listener, who's the one doing the measuring, the wave speed increases. And that's because the wave is traveling towards the listener, but the listener is traveling towards the wave. And so the apparent velocity of the wave coming towards the listener is greater by the amount of the listener's velocity. And so if we write the Doppler-shifted frequency now as v prime over lambda, where v is the new wave speed, v prime is v, the original wave speed, plus the velocity of the listener. So factoring out a v term from the numerator gives us the quantity 1 plus vl over v. V divided by lambda is nothing more than the original frequency, and then in brackets we have 1 plus vl over v. So if we rationalize this over a common denominator, we get a simple expression. F prime is equal to f times v plus vl over v. vl is the listener velocity, v again is the wave velocity. If it were sound, we would use the appropriate value for the speed of sound. And we see again in this equation that f prime is greater than f because the fraction is greater than 1. Alright, so now we've got an equation for the source moving towards the listener and the listener moving towards the source. So if both the source and listener are moving, these two effects that we've considered both occur at the same time. but we can develop a general equation by first accounting for one effect and then the other. So for a moving source, again, f prime is f times v over v plus or minus vs. And remember, we would use the minus sign if the source is moving towards the observer, because that would make the fraction greater than 1. We would use the plus sign if the source is moving away from the observer or the listener, because that would give the fraction a number that would be less than 1, and therefore the Doppler frequency would be shifted downward. So now, to take into account the motion of the detector or the listener also, we take this Doppler shifted frequency f prime that comes from the source motion and put that in here as f prime, and then multiply it by the term that would account for the moving listener, v plus or minus vl over v. So when we make this substitution, now f prime is given by the top equation. We plug it in to the f prime in the bottom equation, and that gives us the original frequency f times the product of these two terms. One accounts for the influence of the motion of the source, which changes the wavelength. The other one accounts for the motion of the listener, which changes the wave speed. And so you have the v terms that cancel out, and we're left with a nicely compact equation. Now, the only thing that we will have to remember when we put this into practice in a problem that we face is to remember the rule. If the motion of the listener is towards the source, that causes the frequency to go up. If the motion of the source is towards the listener, that also causes the frequency to go up, and vice versa. When the motion is away, that causes the frequency to go down. And remembering that will help us figure out whether we should use plus signs or minus signs. And there can be lots of different combinations. We could have a plus in the numerator and the denominator, or we could have a minus in one and a plus in the other, or vice versa. Or we could even have a minus in both of them, just depending on the relative motion. So this equation is valid for all one-dimensional problems, and we will simply have to get practice remembering how to handle the signs. We'll work some examples in class, and I'll see you there.